Hello everyone. In this session, we are going to discuss the concept of ring. In the continuation of the previous session, where we discussed the concept of group. So, if you didn't check the previous video, do check it so that you get clarity about the group. Because ring can be considered as the extension of a group in terms of some property as well as in terms of some operation. Okay, so let us start the today's discussion, which is based on the concept of ring. The first thing is that, as I discussed in the last session, that what is exactly algebraic structure, and we discussed over in the last session that what exactly algebraic structure is. So, a ring is also a kind of algebraic structure where the set is denoted by R. In group, we do have only one operation, which is called as a binary operation. But when talking about the ring, it do have two operations. The first operation I can consider it as plus, and the second operation I am considering is as star. We make sure it's not that plus and star are the only operation for the ring structure. The operation can be any binary operation. So just for sake of representation, I take two operations, one as addition, one as a star, can be considered as multiplication. So this algebraic structure, we called it as a ring if it satisfies certain properties. What are those properties? Let us try to understand them one by one. The first property says that the structure R with the first operation, that is R comma plus, must be a abelian group. Must be a abelian group. And we discussed that what exactly a abelian group in the last section. Now, talking about the second property is about the second operation, and it says that the structure R with the second operation is a semi-group, is a semi-group. And we discussed in the previous session that what exactly we mean by a semi-group. So if that star operation, that is the second operation, satisfy the condition of semi-group, which is closure and associativity, then this structure R comma star we called as a semi-group. The third property is what? It says that uh, the operation star follow the operation star on plus follow the distributive law. That what exactly it means. If I am talking about the distributive law, so what the distributive law says that the operation star, if I take A as the first element and B and C as the second element. So this star should be distributed on addition. That means A star B plus C should equals to A star B and then plus A star C. And from both the side, that means it can also be written as B plus C, or like if I'm writing in the same term, so B plus C star A. Then it should comes out as B star A plus C star A. So this is what we call as a distributive law, and the operation star is distributed on operation plus. That means the second operation is distributed on the first operation. An algebraic structure which follow these three properties, like abelian group with respect to first operation, semi-group with respect to second operation, and follow the distributive law, then we call this structure as a ring. We call this structure as a ring. Be careful, these operation plus and star may be any operation defined in the problem. Let us move on to a problem. So this is a problem where they are asking that prove that the set R, which is having elements 0, 1, 2, 3 and 4, is a ring with respect to operation addition modulo 5 and multiplication modulo 5. That means we are supposed to check the operation which is plus addition modulo 5 and multiplication modulo 5 on R. So, as did in the last session, that when talking about operation, addition modulo, multiplication modulo on any set to check the different properties, like closure, associative, identity, inverse, and commutative, because we are supposed to prove that the set R with respect to first operation is abelian group, and the R with respect to second operation is semi-group. Okay, so what we'll do, we'll make the composition or Cayley table in this scenario for both plus as well as multiplication 5. And on that basis, we'll say that the structure is a ring or not. So let us make a Cayley table, one for addition modulo 5. The element is 0, 1, 2, 3, and 4. And the second is on this side, all the elements. So addition modulo 5, that means the operation is defined as a plus b divided by 5, and whatever the remainder comes out, that is the output of that operation. So 0 plus 0, 0 plus 1, 0 plus 2, 3, 4, 1, 2, 3, 4, 5. When I write 5, and 5 in addition modulo 5 is 0. That means 5 divided by 5, remainder is 0. So this is 2. This is 3, 2 and 2, 4, 2, 3, 5, 2, 4, 6. 6 divided by 5, remainder is 1. Then 3 plus 0, 3, 1, 4, 3, 1, 2, 5, 6, 7. 4, then 5, then 6, then 7, then 8. 8 means in mod 5, it is equal to 3. This is the table for addition modulo 5. Let us make for multiplication modulo 5 too. So in the same manner, the multiplication modulo is the operation when A cross B is divided by 5. When A cross B divided by 5. So if I multiply A cross B, so this is how it looks like. So this is 0 in the first row, everything comes out as 0. Then it is 0, then 1, 2, 3, 4, 0, 2, 2 2s are 4, 2 3s are 6, 2 4s are 8. So I am multiplying and divided by 5. So this will be 0, then 3, 3 2 6, and 3 3 9, and 3 4 12. So 2. Last row 4 0, 4 2 8, 4 3 12, and 12 divided by 5, remainder is 2, 4 4 16 1. So these composition table or Cayley table we needed. Now first thing, what I supposed to prove, that R with respect to operation plus is a abelian group. So as discussed in the last session, can we say the operation is closed or closure property satisfied? The answer is yes, because from composition table we can say for every A comma B belongs to G, I can say that A plus 5 B also in G. Hence the operation satisfies the closure property. Because one more observation is what? In the table, every element is from R, either 0 or 1 or 2 or 3 or 4. In the same manner, talking for second property, associativity. So we know that addition is trivially associative. That means A plus 5, B plus 5C is same as A plus 5B plus 5C. So you can prove it by taking some counter example from the table. ABC belongs to the R structure, not G. In the same manner, the third property, identity element. So we know that in addition case, the identity is 0. Like how I am getting identity as 0? You can see 0 when added to any number, operated to any number, we get that number. That means if I take any A, so A addition modulo 50 is always A, and this is what the definition of identity. Now talking about the fourth property. So fourth property is about the inverse. So from the table, you can say wherever the identity exists, that will help you to find the inverse. What is the definition of inverse? It says that B is the inverse of A if A operated B gives you identity. So just see here, 0 operated 0 is 0. So 0 inverse, we getting as 0. 1 operated on 4 gives it 0. So inverse of 1 is 4. Then 2 operated to 3 gives you 0. So inverse of 2 is 3. 3 operated to 2 gives you 0. So inverse of 3 is 2. And finally, 4 operated to 1 gives you 0. So inverse of 4 is 1. And hence I can say that for every A inverse exists. Talking about the last property, so last property is about the commutative law, and why trivially I can say A plus 5B is same as B plus 5A. The operation is also commutative. So now I can say that since the operation plus 5 for R satisfying the 5 property which is necessary to be a abelian group, which is closure, associative, identity, inverse, and commutative. So hence R plus 1 is a abelian group. Okay, this is a abelian group. In the same manner, if you see that what we did in the last, a ring is what? For the first operation, it should be abelian. Now for the second operation, it should be a semi-group. So semi-group means what? It must satisfy the two property. One is closure and second is associative. So from this Cayley table, you can say every element comes out from R. Like it is either 0 or 1 or 2 or 3 or 4. So that means the operation x5 in R is closed or satisfying the closure property. Associativity, trivially multiplication is also associative. So hence I can say the second property which is about that R with respect to second operation must be a semi-group is also satisfied. Now talking about the distributive. So now as we know that the multiplication is always distributive on addition, that exactly what means, or how should I write it? Let me erase some part from here. So in that case, what exactly we are supposed to show that for every A, B, C, the operation multiplication modulo for every A, B, C, the operation multiplication modulo like this is distributed on addition modulo C. And you can easily verify it by taking A and B and C from the table. Okay, so this is how I can conclude that the distributive properties also hold. So for this structure, by the help of Cayley table, I show that R with respect to first operation is abelian group, and with respect to second operation, it is a semi-group. And also second operation, which is multiplication modulo 5, is distributed on the first operation, which is addition modulo 5. And hence I can say the given structure, which is R plus 5 and cross 5, is a ring. I hope you understand this example. There's a one more example. Prove that the set of all matrices of the form 0, 0, AB, where A and B are the real number with the matrix addition and matrix multiplication is a ring. We are also supposed to check the ring is commutative or not. Does it possess the unit elements or not? I'm leaving it as your practice question. Try to solve it. For right now, let us close this session.